Welcome to chemistry, conjugate acid-base pairs. The concept of conjugate acid-base pairs is fundamental to understanding how acids and bases behave in solution. Developed by Johannes Brønsted and Thomas Lowry in 1923, their theory defines an acid as a proton donor and a base as a proton acceptor. When an acid donates a proton, it forms its conjugate base. When a base accepts a proton, it forms its conjugate acid. These two species form a conjugate pair. This framework allows chemists to predict reaction outcomes, calculate equilibrium constants, and understand relative strengths. In this presentation, we explore Brønsted-Lowry theory, identifying conjugate pairs, amphiprotic water, Ca times Kb equals Kw, and 5 quiz questions and 5 solved problems. Let us begin. The Brønsted-Lowry theory revolutionized acid-base chemistry by focusing on proton transfer. A Brønsted-Lowry acid is any species that donates a proton or hydrogen ion H+. A Brønsted-Lowry base is any species that accepts a proton. This definition is broader than the Arrhenius model because it includes molecular substances like ammonia that do not contain hydroxide ions. Consider the reaction between hydrogen chloride and water. HCl donates a proton to water, producing hydronium ion H3O+ and chloride ion Cl-. HCl is the acid, water is the base. After proton transfer, we have the conjugate base of HCl, which is Cl-, and the conjugate acid of water, which is H3O+. A reaction always involves two conjugate acid-base pairs, the original acid and its conjugate base, and the original base and its conjugate acid. The forward and reverse reactions compete, establishing an equilibrium. Identifying conjugate acid-base pairs follows a simple rule. The conjugate base of an acid is what remains after the acid donates its proton. Conversely, the conjugate acid of a base is what forms after the base accepts a proton. To find conjugate pairs in a chemical equation, look for two species that differ by exactly one proton. For example, consider the equilibrium between acetic acid and water. CH3COOH donates a proton to become CH3COO-. These differ by one H+, so they form a conjugate pair. Water accepts a proton to become H3O+. Water and H3O+ differ by one H+ and form the second conjugate pair. The general rule: subtract H+ from an acid to get its conjugate base. Add H+ to a base to get its conjugate acid. The conjugate base always has one fewer hydrogen and a charge that is more negative by 1. For a neutral acid like HF, the conjugate base is F-. For a positively charged acid like NH4+, the conjugate base is neutral NH3. Here is a summary of important conjugate acid-base pairs you will encounter frequently. For each acid, we list its conjugate base. The strongest acids produce the weakest conjugate bases. Hydrochloric acid, HCl, has conjugate base Cl-, which is so weak it does not act as a base in water. Sulfuric acid, H2SO4, donates its first proton completely to form HSO4-. The second proton has Ca of 1.2 times 10 to the negative 2. Acetic acid, CH3COOH, has conjugate base acetate, CH3COO-, with Kb of 5.6 times 10 to the negative 10. Ammonium ion NH4+ has conjugate base ammonia, NH3. Water H2O has conjugate base hydroxide, OH-. Notice that as the acid becomes weaker, its conjugate base becomes stronger. Hydroxide is the strongest conjugate base here, and its conjugate acid water is extremely weak. Water is the most important amphiprotic substance in chemistry. An amphiprotic substance can act as either an acid or a base, depending on the reaction partner. When water reacts with a stronger acid like HCl, water acts as a base and accepts a proton to form H3O+. When water reacts with a stronger base like ammonia, water acts as an acid and donates a proton to form OH-. this dual behavior is critical because it allows water to serve as the universal solvent for acid-base chemistry. The autoionization of water is the ultimate example. Two water molecules react. One donates a proton acting as an acid, the other accepts a proton acting as a base. This produces H3O+ and OH-. The equilibrium constant Kw is 1.0 times 10 to the negative 14 at 25 degrees Celsius. In pure water, both concentrations are 1.0 times 10 to the negative 7 molar. The single most important principle in conjugate acid-base chemistry is the inverse relationship. A stronger acid has a weaker conjugate base, and a weaker acid has a stronger conjugate base. This follows directly from equilibrium. Consider hydrochloric acid. HCl is very strong and completely transfers its proton. Cl- has virtually no tendency to accept a proton back. The conjugate base of a strong acid is negligible as a base. On the other end, water is extremely weak with Ca of 1.8 times 10 to the negative 16. Its conjugate base OH- is a very strong base. Acetic acid is weak, so acetate is a moderately strong base with Kb 5.6 times 10 to the negative 10. Ammonium ion NH4+ is weak. Its conjugate base NH3 has Kb 1.8 times 10 to the negative 5. For any conjugate acid-base pair, there is a universal mathematical relationship. Ca multiplied by Kb equals Kw, which is 1.0 times 10 to the negative 14 at 25 degrees Celsius. This is derived from the equilibrium expressions. For acid HA, Ka is H3O+ times A- over HA. For its conjugate base A-, Kb is HA times OH- over A-. When you multiply Ko by Kb, the HA and A- cancel, leaving H3O+ times OH-, which is Kw. This is a powerful tool. If you know Ca of an acid, you know Kb of its conjugate base using Kb equals Kw over Ka. For example, acetic acid has Ka 1.8 times 10 to the negative 5. Acetate ion has Kb equals 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5, which equals 5.6 times 10 to the negative 10. Polyprotic acids have more than one ionizable proton and form a series of conjugate pairs. Phosphoric acid H3PO4 is a classic example with 3 protons. First step, H3PO4 donates a proton to form H2PO4- with Ka 1 of 7.5 times 10 to the negative 3. Second step, H2PO4- forms HPO42- with Ka 2 of 6.2 times 10 to the negative 8. Third step, HPO42- forms PO43- with Ka3 of 4.8 times 10 to the negative 13. Each successive Ka is smaller because each proton is harder to remove. Each conjugate base can also act as a base. HPO42- is both the conjugate base of H2PO4- and the conjugate acid of PO43-. Species that can act as either acid or base are called amphideric. Here is quiz question number 1. In the reaction between NH3 and H2O producing NH4+ and OH-, which species are the conjugate acid-base pairs? Option A, NH3 and OH- and H2O and NH4+. Option B, NH3 and NH4+. and H2O and OH-. Option C, NH4+ and OH- and NH3 and H2O. Option D, NH3 and H2O and NH4+ and OH-. Take your time to recall the definition of conjugate pairs. The correct answer is option B. Conjugate pairs differ by exactly one H+. NH3 accepts a proton to become NH4+, so they form one pair. H2O donates a proton to become OH-, so they form the other pair. Quiz question number 2. What is the conjugate base of HCO3 minus? Option A, H2CO3. Option B, O minus. Option C, CO3 minus. Option D, CO2. Remember, the conjugate base is formed by removing one proton. The correct answer is option C. HCO3 minus H plus gives CO3 2 minus. The charge goes from -1 to -2. Option A, H2CO3, is actually the conjugate acid of HCO3 minus, not its conjugate base. Quiz question number 3. If Ca for HF is 6.8 times 10 to the negative 4, what is Kb for F minus at 25 degrees Celsius? Option A, 6.8 times 10 to the negative 4. Option B, 1.0 times 10 to the negative 7. Option C, 1.47 times 10 to the negative 11. Option D, 1.0 times 10 to the negative 14. Use the relationship Ca times Kb equals Kw. The correct answer is option C. Kb equals Kw divided by Ka equals 1.0 times 10 to the negative 14 divided by 6.8 times 10 to the negative 4, giving 1.47 times 10 to the negative 11. Kb is much smaller than Ca, confirming HF is a stronger acid than F minus is a base. Quiz question number 4. Which of the following is the strongest conjugate base? Option A, Cl minus, conjugate base of HCl with Ka approximately 10 to the 7. Option B, CH3COO minus, conjugate base of CH3COOH with Ka 1.8 times 10 to the negative 5. Option C, F minus, conjugate base of HF with Ka 6.8 times 10 to the negative 4. Option D, O minus, conjugate base of H2O with Ka 1.8 times 10 to the negative 16. Remember the inverse relationship. The correct answer is option D. The weaker the acid, the stronger its conjugate base. H2O has the smallest conjugate base. H2O has the smallest conjugate base H2O as the strongest conjugate base. Quiz question number 5. In the reaction HSO4 minus plus CO3 minus giving SO4 minus plus HCO3 minus, which species acts as the acid? Option A, CO3 minus. Option B, HSO4 minus. Option C, SO4 minus. Option D, HCO3 minus. Remember, the acid is the proton donor. The correct answer is option B. HSO4 minus donates H plus to become SO4 minus, so HSO4 minus is the acid. CO3 minus accepts H plus to become HCO3 minus, so it is the base. The conjugate pairs are HSO4 minus and SO4 minus, and CO3 minus and HCO3 minus. Problem 1. Identifying conjugate acid-base pairs. For the reaction HNO2 plus CH3NH2 producing NO2 minus plus CH3NH3 plus, identify the two conjugate pairs. First, look at HNO2. It loses H plus to become NO2 minus. So HNO2 is the acid and NO2 minus is its conjugate base. Second, CH3NH2 gains H plus to become CH3NH3 plus. So CH3NH2 is the base and CH3NH3 plus is its conjugate acid. The two conjugate pairs are HNO2 and NO2 minus and CH3NH2 and CH3NH3 plus. Remember, conjugate pairs always differ by exactly one proton. Problem 2. Finding the conjugate acid from a base. Write the formula of the conjugate acid for each base: NH3, H2O, CO32-, and PO43-. To find the conjugate acid, add H plus to each base. NH3 plus H plus gives NH4 plus. The charge goes from 0 to +1. H2O plus H plus gives H3O plus. CO32- plus H plus gives HCO3-. The charge goes from -2 to -1. PO43- plus H plus gives HPO42-. The charge goes from -3 to -2. So the answers are NH4 plus, H3O plus, HCO3-, and HPO42-. Problem 3. Finding the conjugate base from an acid. Write the conjugate base for each acid, HBr, H2CO3, NH4+, and HSO4-. To find the conjugate base, remove H+ from each acid. HBr minus H+ gives Br-. H2CO3 minus H+ gives HCO3-. NH4+ minus H+ gives NH3. The charge drops from +1 to 0. HSO4- minus H+ gives SO42-. The charge drops from -1 to -2. The answers are Br-, HCO3-, NH3, and SO42-. Remember that removing H+ leaves the conjugate base with one fewer hydrogen and charge 1 unit more negative. Problem 4. Calculating Ca from Kb. The Kb of nitrite ion NO2- is 2.2 times 10 to the negative 11. Calculate Ka for its conjugate acid HNO₃ at 25 degrees Celsius. Use Ca times Kb equals Kw equals 1.0 times 10 to the negative